Hello, good afternoon. We are Tala. Today, we will be presenting our prototype implementation of a tsunami early warning system. So the first tsunami reporting system was deployed in the Pacific Ocean 20 years ago in the form of the DART system. Currently, a global network of more than 60 systems is established. However, they are expensive and difficult to deploy, and also expensive to maintain. The Philippines is not new to the tsunamis. Due to our geographical location in the Pacific Ring of Fire, an earthquake-induced tsunami is quite common. Some of the notable events occurred in 1828, 1934, and 1999. Having a local system is important since the tsunami sources in the country are studied to be as near as 100 kilometers from the shore. Without any warning system in place, there is little to no warning for people nearby to evacuate. In the Philippines, there is some existing effort to implement some form of tsunami detection systems, but mostly they are very simple, manual, and quite ineffective. As an example, in the southern part of the Philippines, they have a video camera monitoring coastal areas. Unfortunately, this involves actual people manually monitoring the video, resulting in labor-intensive, error-prone detection of tsunamis. To hasten the response and mitigate the loss of lives, our team at Tala proposes putting up a cost-effective buoy network around the country. The network will consist of a land station, a master buoy, and support nodes. This is a visualization of Tala buoy. This was inspired and aimed to be based on the meteorological buoy deployed by the Philippine Department of Science and Technology way back in 2013. Inside that Tala buoy are the SPRESense main and extension boards. Aside from this, we plan to complement this with some measurement and weather sensors in the future. We've studied important locations in the Philippines that are prone to tsunamis. These locations are proposed to be the initial locations of the Tala buoy network. Points that were considered are the coastal population of the area, critical infrastructures for supply chain, and economic significance of the nearby countries because of tourism industry. To give more understanding about the implementation style of our buoy network, here is a two-dimensional representation. X-axis as the distance from the shore, y-axis is the shoreline. The sinusoidal curve represents the ocean waves. Our buoys are spaced together 10 kilometers away from each other so that they could still communicate through a wireless network. In this case, our master buoy is master node is buoy 3, and other buoys are support nodes. Support nodes include a SPRESense receiver. They receive data which is parsed and they also evaluate the raw data by itself. Data is then sent to the master buoy for further processing. Master buoy, on the other hand, has its own, again, SPRESense receiver, but not only that, it receives also data from the support nodes. All these data are collected and processed to determine whether a tsunami event is happening. In the future, we plan to include weather sensors, camera imager, and hopefully to improve tsunami detection, land stations are expected to perform machine learning modeling. For this demo, we have prepared a wave propagator showing tsunami dynamics and virtual buoys. The Multi-GNSS data from the propagator is parsed. 5 data sets from 5 buoys are accepted by our master node. However, there is an option to receive data from live QGIS feed, data streams, or pre-recorded tsunami data. For demonstration purposes, the LEDs on the main SPRESense board were programmed to act as the tsunami alarm indicators of the buoy network nodes. A lighted LED means an imminent tsunami is being detected by a corresponding buoy node. At the start, calm waves are expected, but once the amplitude of the wave height increases, we expect that the buoy warning is triggered. Here, you can see that the buoy support node farthest from the ocean is the first one to sense that a potential tsunami is coming, sending alert to the other nodes. Now, as the tsunami progresses and more buoy nodes are detecting tsunami, the master node is expected to start sending a EWS message to the land station. The land station will be in charge of verifying the data and broadcasting this to the affected people in the locality. Affected communities will receive SMS messages that include event warning and source. Further details can be checked through our downloadable phone app. The app shall show important details, including the nearest evacuation site. Through the app, you may be redirected to a third-party app that can provide driving directions, live traffic, and road conditions. Now, finally, all of this, when implemented into the proposed locations, the buoy cost-effective network will give us 10 minutes of advance warning for people to evacuate, 5 times reduction in the development and implementation cost, translating to millions of dollars in savings. And finally, most importantly, implementation of this cost-effective buoy network will lead to thousands of lives saved during tsunami events. So in the end, I encourage all of you to help us bring this cost-effective buoy network into reality. As Helen Keller said, alone we can do so little, together we can do so much. Thank you again, and together, let's make a difference. Thank you.